it'll get more on topic with interconnects, but I've been working more in the space of microscale interconnects. So this is for systems on chip and but also co-packaged optics. And this does, I promise, connect into the future of interconnects. But let's get started here. All right. So let me minimize this guy here. There we go. So, a lot of people have, pointed out that, Moore's law is starting to taper off. We're already seeing the signs. This is the Hennessy-Patterson diagram, but if you actually paid careful attention to Eric Strohmeyer's top 500 analysis, that we're starting to see that signal appear in the top 500 list. This is, for the past 3 decades, and this is, of course, for all the flaws there are in the LINPACK benchmark, it has tracked Moore's law, where every decade we see a 1,000 times improvement in computer performance, both for the top machine in the list, for the bottom machine in the list, and the summation of all of the machines in the list. And so that shows a very, very consistent curve, log linear plot showing exponential growth rate. This is the plot that he showed this time around, whereas this used to be, we would be, in 2030, we would be at 1,000 exaflops or a zettaflop if things were business as usual. The projection now is that we're only seeing 10x performance growth every 10 years instead of 1,000x performance growth every 10 years. So the signal has become very clear even for the largest scale systems. And also, by the way, the last machine in the list has been exactly the same for 2 years, 2 years in a row, which is also that's unprecedented. So, there's what's really happening here is that, our entire economic model for growth in computing performance is based on a transistor focus, as you can see in the right here. Is that working? Yeah. And so these are diagrams from the Heterogeneous Integration Roadmap, which is an industry IEEE project, but also Neil Thompson, who donated these figures. He's an economist and computer architect at MIT. And so Neil's diagram here shows that, we had been an economy, a microelectronics economy based on you shrink the transistor, you get improved performance at a lower cost, which leads to market growth, which in turn leads to reinvestment. And this was our virtuous cycle for 50 years plus. We can no longer focus on the transistor to carry us through and deliver these 1,000x improvements every 10 years. Now, the only game in town in terms of pushing things forward is to go with a system focus, where it's really the system level delivered performance for your target workload or applications is going to be your metric for success, and which leads to increased functionality at a lower cost, market growth, investment, and again, focus on the system behavior, it's no longer shrinking transistors. And to achieve that, this is a paper written by Neil and a number of other MIT faculty in CSAIL, where it's really, they see software, algorithms, and hardware architecture co-designed together is the only path forward for the broader microelectronics community, not just us in HPC. And there's 3 really great articles that you can go to neilt.com and see, but they've got economic analysis, but also technical analysis of the alternative paths and why we believe that this is true. In fact, this trend has already been happening. First, of course, in the mobile and embedded space, where you had a fixed swap, you're basically power limited, you want to get more battery life in the same sized package, maybe even a tinier package. And this is a dye photo that was taken of the Apple A8 chip, and you can see already about half of the chip area is dedicated to out-of-core accelerators. That was 29 different heterogeneous accelerators in 2016, but if we fast forward to today, 2/3 of the chip is covered in the specialized accelerators, 40 plus. Why is Apple continuing on this? Because it works for them. It makes them revenue, makes them money. And, you know, so this, you know, I've heard a bunch of people at this conference say, oh, that's a terrible speculative idea that we should go with heterogeneous acceleration. Extreme heterogeneity is really stupid because it's going to be hard. And the answer to that is, you know, it's not speculation. This has already happened like 10 years ago. We're just catching up to the trend. The question is, can we be ready to exploit this? And we've been so caught up in other pursuits that we have not been paying attention to what the state of the art really is right now. You can see that the functionality of these dedicated hardware blocks, though, are focused on echo cancellation, denoising of images, lots of stuff that is kind of cool for a cell phone, but not very, we can't repurpose it for us. So the GPU, you know, it did dense matrix algebra and FFTs like nobody's business, but that was fortunate that graphics needed some of the core operations that we also need for HPC. That we're far less lucky with what's currently in the cell phone chips. But you know, even the mega scale data, the hyperscale data centers are doing this. So you've seen the Google TPU. If the operation that the TPU was specialized for was something we actually needed for HPC, then we would have had a 3.5 megawatt exaflop system back in 2015. But unfortunately, it isn't the algorithm that we need. But it gives you an idea of that we're talking about 2 orders of magnitude. And also that's in the way back machine. In 2015, we were thinking that an exaflop in that technology node would have been a gigawatt. and so to deliver that kind of performance in an accelerator shows you how much headroom there, in an obsolete technology node for that matter, 28 nanometer, just shows you how much headroom there is to gain from specializations. And you know, this isn't just a hardware architect screen. Well, it's already happening, but specialization is nature's way of extracting more performance in a limited environment. So in the past, we've had powerful general purpose processors like the Xeon and the Power, giant Raptors when there's a food-rich environment. But then when there's food scarcity, and I'll compare food scarcity to Dennard scaling ending in 2004, then you end up with many lighter weight birds, like a couple of dozen, you know, really aggressive sparrows here, which is kind of what Knight's Landing was. And to some extent, GPUs and some of the early ARM architectures from Cadmium and Marvell. If you have even further food scarcity, then the critters got to go after different food. And you can see from the Darwin birds here, they're being specialized to the different food sources that they specialize, that they're pursuing. And this is kind of where we're going with post-Moore's law scarcity. And we're seeing this already manifesting at Apple, Google, Amazon, the hyperscale data centers. So, you know, that's our future, going from homogeneous to many core to many core plus GPU acceleration to many different kinds of acceleration and many different kinds of memory technologies. You see the Optane memory sitting side by side with DDR and HBM in the same node. This heterogeneity is already with us, and you've also seen on the show floor here, probably from some talks, all of the really kind of novel data flow is back, baby. You know, you see GraphCore, you see Samba Nova, lots of what used to be novel architectures that we forgot about for a while, they're all coming back. And you know, the question is for HPC, our market, not the hyperscale data centers. You know, I believe in the if you can't beat them, join them thing, but we should do that in the same way that we did with the attack of the killer micros. Attack of the killer micros, it wasn't, let's just use the same servers that, you know, people are, you know, using in their desktop. We modified them, we augmented them with an 80-20 rule to modify that 20% that made the difference for HPC while retaining the 80% that is supported by an enormous market. So I'm not saying we just buy stuff from the cloud or buy it from a hyperscale data center. I'm saying we understand the economic model that underpins the hyperscalers and leverage that economic model to serve the HPC marketplace. So the key questions for us are, what are the right specializations to include? You don't want to just take specializations off the shelf that were designed for echo cancellation and try to repurpose it for a PDE solver. I don't know how you do that, but somebody might be that clever. What's the cost model? We know we can't afford to spin our own chips from scratch. So that's off the table. So how do we leverage the supply chain that the hyperscalers are creating for themselves? And you have like the ARM and the embedded ecosystem there. It's the first shoe is already dropped. IP is the commodity, not the chip, because the IP, the creation of a circuit design and validating that it's correct is by far the most expensive part of fielding a new chip. Software and all the other stuff is expensive, but those are the dominant costs. The ARM ecosystem is about sharing that cost across multiple markets by reselling the same design to the HPC market, to other server markets and other verticals. And but I'm also going to talk some about, we've gone beyond just IP being the commodity being our economic model. There's other partnerships and economic models that can serve the future of HPC. So let's take a look at the hyperscale data center strategy. I'm going to start with the interconnect on chip. I do like to talk a lot. I hang out with Karen Bergman. I've drunk the Kool-Aid. I believe in co-packaged optics. But people say, oh, so you want photonics everywhere? And it's like, no, where electronics still works, you want to use electronics. It's cheap. So do it. So we'll start with the interconnect on the chip part and work our way out to the what the interconnect would look like for the data center in the future. So, going back to the specialization thing, this isn't just something that we in HPC, we want to specialize a machine to serve HPC workloads. This is also an observation for the folks that are in the hyperscale space. This is from Dharmesh Jani when it was still Facebook, now Meta. I hate that name. That we had the early compute era where it was the universal computer. You got your C++ and your MPI. It does it all. Facebook saw, and this is the current era where we have co-processors for graphics, now AI, machine learning, and they've already created specialized clusters. A different cluster for inference than for training, a different cluster for database and storage to serve S3 than the one that they use to actually then connect to S3 and do data processing on it. Their vision for the future in hyperscale is to be able to reuse the same building blocks, but arrange them to customize, tailor a machine for subparts of their workload. And that is the hyperscale data center strategy for the future. Is again, not a transistor focus, which leads to a universal machine, but a system focus, which is how do I deliver value to the workload? How do I deliver more cost effectively? So this is the why. This is a diagram from our good friend Dan Reed, and this is why you should be concerned about what the hyperscalers are doing and why they're doing it and how they're doing it. And how they're doing it is chiplets, but I'll tell you, why you should care, and that's that it's no good any longer to just talk about technology. You have to understand the market context. And this is the market context diagram from Dan, which is to recognize that we've always, ever since the attack of the killer micros, we've been partnering with Intel and IBM and stuff, and they're great people and all of that. They were the microprocessor suppliers. And so they are the right people they were the bottom of the Branscombe pyramid that I have to the lower right here. And we've relied on that for 30 years. But now you look at who's actually in control of the microelectronics market, and it ain't the guys over in blue. It's the ones in the green here. And they're making their own chips. Pat Gelsinger, when he first came in, yelled at his, engineers that, Apple's making its own chips instead of using ours. We've been outdone by a lifestyle company. That's how bad it is right now. So he's cleaning house and getting into the chiplets thing, but the new bottom of the Branscombe pyramid is for us to understand the supply chain the hyperscale data centers are creating to serve them and leveraging it, not just, taking the pieces, parts that come out, figuring out how to do the 20% that makes sense for us. while having this market in the green supporting the bottom of our Branscombe pyramid. And so what we're seeing is this, there's two different teams forming. One is called ODSA. ODSA is an open domain specific system architecture. It's creating standards for chiplets, die-to-die interconnect standards for the chiplets so that you can compose them together into custom machines for your liking. The other is UCI Express, and this is an effort led by Intel but has a lot of the traditional companies, IBM, Xilinx and stuff, and AMD joined in on that one. Both are, it's not just, licensable IP, that was a good first step, but this is also that leverage the economic model, licensable IP and assembly by a third party. So this isn't just licensing the IP and then having to lay out a chip. Because laying out a chip is still expensive, not as expensive as the IP that goes in the chip, but it's still expensive. Here you have a third party who actually, like Ventana, for example, who creates server class ARM cores pre-spun on a chiplet that you can then combine with HBM if you want HBM, or can combine with DDR if you want DDR, and it's all a matter of which chiplets you plug in. We can recreate Fugaku for a fraction of the cost of what it costs to develop Fugaku, but by taking these off-the-shelf chiplets and combining them together, because the cost of packaging is way lower than the cost of spinning those chips. So this creates an environment where there's a smaller incremental cost for HPC to play. Because again, it's the 80-20 rule. We need to focus our open efforts on what uniquely benefits HPC, support this Branscombe pyramid for interoperability and sustainability. But this is a diagram that that Dan showed in his blog. We're too small to attack the city anymore. So we have to understand, come up with a different economic model so we once again are in position to attack the city. The reason why this works with the chiplets and stuff too is that once, with Moore's law tapering off, once you create a chiplet, that lifetime for that chiplet is far longer. The useful lifetime for that chiplet is far longer than it used to be. And so what we're seeing is ever since the Dennard scaling tapered off, once they create those IP blocks, then you get to reuse them over and over again. You can keep on reaching into that chiplets drawer, and we're looking at 90% reuse of IP blocks already. And that's how you amortize that initial cost of creating the first version of that IP. If I create a really great thing for block for PDE solvers, I can reuse it again. I can augment it and add to it, but the base cost of I have an accelerator for PDE solvers gets you to you can reuse it over and over again. So I forgot to mention, what's a chiplet here? The chiplet is basically right now for pins on a chip where we have limited bandwidth to get off of the chip. And that was the complaint of the first GPU systems. I had to cross that damn PCI bus, and it's a fraction of the speed of DDR, much less high bandwidth memories. But the problem was that I have a limited number of pins in a chip. The pin pitch for a chip today is about 0.8 millimeters, and 2 decades ago, the pin pitch was 1 millimeter. So not much improvement over a decade. What they are able to do with these little solder micro bumps and now copper micro pillars, what we've been doing to make up for the fact that we couldn't increase pin density is we've been increasing SerDes rates. And now we've got 100 gigabit per second SerDes, and it's ridiculous. It's totally the opposite of Dennard scaling, where we ended at 1 gigahertz signaling rate. So this is doing what we've been doing for years in HPC, is recovering performance through parallelism. So these solder micro bumps are 100 times more dense than the pins in the pin package. And now we can slow them back down and operate at 1 gigahertz to 5 gigahertz data rates, which is much more compatible with where Dennard scaling is. And so chiplets is basically using these little copper micro bumps. You can etch the wires on a silicon substrate, and that's actually fairly inexpensive to actually do those wire patterns on a silicon substrate. You just flip chip, the top of the chip onto that silicon substrate, and those copper micro bumps ionically bond to the underlying metallization layers, and you can connect these chiplets together. And on a silicon interposer, they have organics now too, but that are cheaper. But that's the baseline chiplet, is using silicon interposer. And the key is to standardize the die-to-die interconnects, both the pin patterns for these little soldered microbumps, the impedances, but also the protocol that you use to speak between them. And that's exactly what the hyperscale data centers are doing. So, how do chiplets enable us to create specialization? There's a lot of stuff on the chip that's just boring. I have to have a core that runs on operating system. I need a memory controller. Maybe I want an NVRAM controller on board, or PCIe. Regardless, there's lots of reusable stuff that you just have to have on every single chip. So you have commercial IP, support that. ARM could create chiplets and supply us. We can have reusable function blocks. We create an FFTW chiplet or a BLAS chiplet. And after you create the FFTW chiplet, BLAS chiplet, you can reuse that for many different designs. And then for big data movement, image processing, machine learning, high speed, co-packaged optics. This modularity enables us to target a wide variety of custom solutions using reusable commodity parts. And the vision that the ODSA has, for example, is an open chiplets marketplace. So what they're working on, and this is again funded by Meta, Google, ARM, Microsoft, not AWS. I don't know what's up with AWS, but anyways, a lot of hyperscale data centers are developing the standards for this die-to-die interconnect, so the chiplets can be used across different vendors. We all know that AMD is using chiplets, but they're using them internally. Intel is using chiplets, but it's all internal. If we can externalize this, then we can mix and match the best stuff from Micron and Intel and NVIDIA through this commodity marketplace of chiplets. And they're afraid enough that they're also they have teams that are joining ODSA meetings and also UCIe meetings to make sure that they're prepared for this because they're worried about it. But you see the size of the hyperscale data centers and what they want. This is what they are doing strategically to get what they want. We need to figure out how we can leverage that too. So they're doing open die-to-die interface standards. They're creating reference designs so you can see how this all works end to end, and also reference workflows, which is how do I go from a chiplet to a package? What's the supply chain to take that chiplet, finish it, and put it together in a package with some third party's chiplets? All of these things are being worked on simultaneously to create this chiplets marketplace. And there's a lot of co-sponsors, but one thing that's clear is that most of the hyperscale data centers are co-sponsors of this because, again, they want those specialized data centers, and so they're investing in creating that future. So now we want to go to the final part, which is breaking out of the chip. I don't have much time left, do I? Or yeah, it's okay. 5 minutes. Okay, I'll get through this. Yeah. So that was inside of the chip, but the other part is breaking out of the chip, co-packaged optics and for resource disaggregation. So this is also what's hurting the hyperscalers. I'm in an ARPA-E project with NVIDIA and Cisco and Microsoft Research. And what they say is happening in Facebook, and so what they're saying that's happening in their data centers, they have one cluster for training because they get this big ass DGX nodes. They cross-connect them with NVLink in order to share the weights or the vectors for the weights, I guess, gradients. And you need that in order to scale up your training workload. But when you go to inference, you don't need to have any GPUs speak to anything. They want to speak to the outside world. You want to stream that data through that trained model in your GPU. And so completely different node design. So the TPU cluster is strictly inference, or the old ones were. And so it's purpose-built for inference, and that's another cluster, another rack. Data mining, they have tons and tons of NVRAM, basically S3 co-located in the same rack with the compute units. And for graph analytics, we need a ton of HBM and for really fast system-wide random access. These end up being separate clusters, and this, if you underutilize one of those clusters, then it's just wasted resources. You bought it, so it's capital cost. It's sitting idling on the floor, so it's ongoing costs for the power. This is another view of it. So from NERSC, we looked at the memory footprint of the workload, and there is 15% of the workload that needs most of the available node memory. And so we know that we have to have high mem nodes, but the vast majority, 75% of the jobs use less than a quarter of the memory in each node. So that means that if I could slosh that memory around, I would only have to have bought 1/4 of the memory that I put into the system. And as you know today, memory is crazy expensive and it consumes a lot of power when you're not using it. And yet 75% of the memory in our systems we are not using at any given time, any given moment. So the hyperscale data centers have gone to this mode of operation called disaggregation. So instead of having a server like our Summit system where we cram anything that you think you might need in the node, we put it into every single node. We got SSD in the node, we got GPUs in the node, we got powerful CPUs in the node, and you put it all in there just in case you might need it. And you replicate and repeat, and then you try to stabilize it. So sorry, that was a joke about we all know how hard it is to stabilize large systems. It's not unique to anybody's system. So so in a disaggregated rack, you basically pool your resources, SSDs, your memory, your high bandwidth memory, and your high capacity memories, GPUs, CPUs, and then you compose them together, pool and compose, to create the node that is in one of those configurations that would otherwise have been a separate rack. They are doing this today, though, with inferior technology. The disaggregation solutions that are commercialized today or internal to Google use 100 gigabit Ethernet or PCIe switches. This is a factor of 10 to 100 off from the bandwidth that we need for the memory technology. So we want to get to 100 gigabyte per second or terabyte per second bandwidths, but it's really hard to break out of the chip at those bandwidths. And the reason why, this is what I was talking about earlier, I moved the slide to the wrong place. These are the pins. There's no Moore's law for pins. It never has been. It's been Rent's rule, which is, like a 1.2% per year growth rate in the number of pins, whereas it is 40%, compounded annual rate of growth for Moore's law. So we made up for it by exponentially increasing the signaling rates. It's gotten to the point now, though, that the power consumed by the signaling to go off chip is now at parity with the power for the compute that's on the chip. There isn't any good place to go from that, and that's why there's so much interest in photonics technology. And so, the thing that's exciting with photonics and this co-packaging, these chiplets, is this impedance match. So as I described earlier, wide and slow, it's learning the lesson of parallelism that we had in our massively parallel clusters. Instead of increasing the signaling rate, we increase the pin density. And if you visit the Heterogeneous Integration Roadmap, which is the industry website, a pretty competitive effort to lay out what the roadmap is for improving this co-packaging, they show 5 consecutive doublings of bandwidth density available. So that's 10 years of Moore's law, but for bandwidth density improvements, is achievable with technology that we already know about today from INEC, and it's been demonstrated in the lab. And they have this roadmap laid out for 5 consecutive doublings so they can line up their manufacturing supply chain, because it takes that long. So this is all doable, and there's a roadmap for it. It's wide and slow, copper pillars 10 gigabits per second. That happens to impedance match with silicon photonics that never got off the ground, because we go up to 100 gigabit SerDes, and then we kick it back down to these rings that operate optimally at 10 to 20 gigabits per second per ring. Now with this co-packaging, now it's impedance matched. I don't have to go high SerDes and then back down again. I can go straight to the rings, directly modulate. I can get hundreds of frequencies of light onto a single fiber, each encoding data at 10 to 20 gigabits per second. Wide and slow. That's the story there. And then the last thing, and this is the most recent, and this is the game changer in the past just 3 years. If I had to have 100 different indium phosphide lasers, each at a separate frequency, that's a showstopper in terms of manufacturing and assembly. Recently, it emerged very efficient, so 30% wall plug efficient cone laser sources. So a single laser that can produce a cone that has hundreds of frequencies of light. Now it all comes together, and I can, instead of having this prime real estate where I have limited area to place my high bandwidth memories, and that's why we have such low memory capacity for GPUs, is because there's limited real estate to array these things around. Instead, I could use that same site, not the same protocol, but the same site to put down a photonics. And once you go, the reason why this is prime real estate is because with that kind of bandwidths, you can only reach 2 centimeters before the resistance kills you, and then you're done. But once you go convert from the electronic to the photonic domain, you can go anywhere in the system, and there's no additional cost for you. And that's why you want to go to photonic. That's the value proposition of photonics. Now I can break out of the package at high bandwidth memory bandwidths. I can have an optical circuit switch, a cheap one that only reconfigures every millisecond or so, and I can patch in the resources that I need to serve the workload that I have. And so now, I can configure for training, have the same pool of resources. I can configure for training nodes, or I can configure for inference. And we've estimated from just workload analysis data from a production supercomputing center that we can reduce the total amount of resources we need to buy by 3/4 and still serve the same workload. So 0 reduction in throughput for the workload, but a whole lot less resources. But more importantly, when we go to extreme heterogeneity, instead of having to pack the same cookie cutter accelerators in every node, even though not all the jobs needed, we can actually patch them in on an as needed basis and actually right size those resources at a rack scale. So I'm going to end there. This is our project, and thanks for listening.
John, thanks for the very insightful talk. We'll have time for a few questions.
So, I understand that.
DK, may I have the question?
Yes, Daisuke, just yeah, you want to go ahead?
Oh, okay. Sorry for the noise because I'm almost boarding to the Frankfurt. But anyway, thank you very much for a great talk, and I'm very curious about how to standardize the interface between the multi-vendor chiplets.
How to, I think the question was how to standardize the interface from between various vendor chiplets.
Yeah, that is the big ticket item, and it's not going to come easy. So both UCIe and ODSA, that's actually at the very core of what they're working on. The things that you have to agree upon for all this to work is the pin pitch, the pin out, and the impedances, and then the protocols. Bundle of wires actually has gotten a number of demonstrator chips that use for protocol PCI Express and AXI, ARM AXI as the protocol standard. And they've also worked the software stack all the way up into Linux and the application. So they have the software stack from the hardware all the way up into the software. Going down, though, the challenge is getting everybody to agree on, it's just like compatibility of pinouts on a microprocessor chip. So you got to agree which signal is what with these little micro arrays of solder bumps. Fortunately, with the solder bumps, though, there's only a handful of companies who can actually create micropillars and solder bumps. So they are in and of themselves the standard because you can only go to TSMC and Intel to do that. And so from a physical perspective, those are standards by default. But the impedances and the protocols that go between those and the pinouts that go between those, that is going to require a lot of compromise between the different players who are playing in this place.
Thank you.
Okay, thank you.
Yeah.
I love it. Thank you.
Yeah. Thanks, Daisuke. Have a nice flight.
Yeah, have a
So
nice
you are
flight.
here and went
Yes,
back.
I'm boarding in 1 minute.
Yeah. Okay. Let's. Anybody else has any questions? Yes.
So Do you think there are enough examples for this specialized IP? So if you talk about echo cancellation, so it's quite natural that this has to be inside such a device, and I would assume the other examples are similar. But do we in HPC have enough examples which are, say, good enough for specialization, so that it's that you get a benefit compared to, say, an FPU or stuff inside a GPU, but well, it widely enough used in HPC so that it makes sense?
Yeah, so the answer is no. Our research program has been checked out for the past 5 years. Had we, GPGPUs used to be like a really wild and crazy idea. And it was 10 years of GPGPUs before we understood it well enough that we were able to field our first GPGPU-based system. That never would have been in the cards were it not for the 10 years of understanding all of the avenues and the benefits and the pitfalls. I have a very low bar for starting, and that bar that I've been using to benchmark different companies and their solutions is, say, recreate Fugaku for me, but do it for less than 100 million. And that's been the challenge. And there's a lot that said, yeah, and they have a spreadsheet. In fact, it's online that if you go to ODSA, go to their spreadsheet, you can plug in the numbers and you can see Fugaku and how much it would cost. And it's nowhere near $100 million. So, so I have a very low bar for specializations. Damn it, I just wanted a freaking ARM core with SVE and a high bandwidth memory. Nobody would fucking give it to me, and except for Fujitsu, and that was off the table. So, yeah.
Yeah.
Let me come back quickly to the question of standards, right? And is there any upcoming standards when it comes to the level of optical interconnect? And then my question is also related to this effort called Gen Z.
Yeah, Gen Z.
Yeah, and I don't know whether Gen Z is still existing or already dead, but it appeared pretty similar. It looked pretty similar to what you have on your slide 3, right?
It's kind of an X-parrot. No, if you ever remember that, the Monty Python. No, it's UCI Express, and well, CXL. Okay, so let's take back a step. CXL basically created a superset of Gen Z. For better or for worse, they said, oh, that's a nice feature that we don't have. Well, if we adopt it, will our big tent be big enough that you would crawl under it? And the answer is everybody's slowly slinking under the tent because it's hard to go against, having all the companies lined up behind CXL. CXL, the danger with CXL is that it is pretty big, heavyweight, I have to say, but on the flip side, it's also built on top of the PCIe physical layer, which is, it's no small matter the engineering that goes into the PCIe, so it's hard to ignore. What CXL is actually doing is PCIe, but they corrected the memory consistency model, so now you can run cache coherence and stuff under it, just like Gen Z was planning and doing. And so I think it's kind of superseded Gen Z, and we are thinking in terms of CXL being the virtual protocol.
What you're basically telling is that CXL has already reached a critical mass that there's no way around it, right?
It cannot be ignored. Like, I would say that the bundle of wires people supporting AXI as an alternative is really important, because the size of the macro for CXL is way, way bigger than AXI. I mean, AXI's so simple. That's been the big bitter pill with CXL, is that you're bringing in a lot of complexity, but somebody else has engineered all of that nasty physical layer stuff that you don't want to do either. So you're really torn. Do I take this behemoth, but I don't have to engineer a bunch of stuff?
Okay, so with this, let's thank again, John.